We are on page 98 in the book, and we're going to look at today distributions. Okay? Now, distributions, sometimes I wonder why I actually have to go through this, but it's sort of laying the groundwork, okay? This is one of those things that I have to go through that sort of makes other stuff a little bit more understandable, okay? If you sort of got that in your mind ahead of time, then it makes it a little bit easier to swallow kind of thing. So reading on page 98, previous page you used graphs to analyze data and calculate the mean, median, mode, and range. Now yesterday we talked about the mean, median, and mode. We didn't talk about the range. Everybody know what the range refers to?
The numbers of the
Sort of. It's actually the difference between the highest and the lowest. So sort of. You're in the right ballpark. In chapter 1 you study probability. In this chapter you will combine these concepts to work with probability distributions. So probability and stats generally go together. If you ever take a university class in statistics, it's usually called probability and statistics. They sort of go hand in hand. A probability distribution gives the theoretical probability for each outcome of an experiment. I'm going to read that again. A probability distribution, so that's what we're looking at today, is distribution, gives the theoretical probability for each outcome of an experiment. We've done this already. When we did the theoretical outcomes, we did those tree diagrams with the head and tails and stuff like that, we were looking at a distribution. Okay? So investigation 1 there says constructing probability distributions. When 4 coins are tossed, what is the probability distribution for the number of heads? Okay? We've done these. We're just going to take it one step further. So part 1 says use a tree diagram to list the sample space for this experiment. I left you a little bit of space there. So let's just tuck this in the corner here. 4 coins are tossed, probability distribution for the number of heads. Okay, so we're going to do our tree diagram. So squeeze it in if you can here. So we're going to go heads, tails, heads, tails, heads, tails, and so on. I sort of ran out of room, but I think you get the picture, right? Let's see if I can squeeze them in now that I'm... Who said that?
Huh?
Did you say that?
I said back probability.
Okay, so we have our tree diagram. It says use the tree diagram to list the sample space for the experiment. We've got it. To construct the probability distribution, fill in a table like this one, list all outcomes in the sample space in the first column. In the second column, enter the theoretical probability of each outcome as a fraction. Do not reduce the fraction. So right here, now I've already done it for you, the left side, the outcome. So all the possible outcomes are 0 heads, 1 heads, 2 heads, 3 heads, and 4 heads. Why did I count heads? Because the question said, what is the probability distribution for the number of heads? So you can either get 0, 1, 2, 3, or 4 heads. Okay. How many total are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So everything's out of 16. Right? Everything's out of 16. We are making a probability distribution. A probability distribution. Okay, so how many ways can you get 0 heads? There's only one, right? Tails, 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 tails. There's only one. One way to get 0 heads. And I'm stroking that one off so that I can keep track of it. How many ways can I get exactly 1 heads? Tails, 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 heads, tails, right? 1. Tails, tails, heads, heads, no. Tails, heads, tails, tails is another one. That's 2. Just those 2 there, right? Or I could have heads, tails, tails, tails. So I have 3 ways to get 1 head. Am I right? Hopefully. That's not 1. That's, oh, this one here, tails, 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 heads. That one there. That should be a 4, shouldn't it? Thank you. 4. 2 heads are usually better than 1. Thank you. I'm here all week. Tell all your friends. That one there, right? 1, 2, 3, 4. Oh, I missed this one here. 5. There should be 6. Did I miss one? Oh, right there. 6. Now, would 3 heads be equal to 1 tails? It's the same thing, is it not? Would 1 tails be the same probability as 1 heads? It would. So this should be 4. And in fact, if you count, there is 4 more. 1, 2, 3, 4. And 4 heads, right there, 1. Okay, so 1 out of 16, 4 to 16, 6 out of 16, 4 to 16, 1 out of 16. Do they add up to 16 out of 16? 1 and 4 is 5, and 6 is 11, and 5 is 16 out of 16, right? Should they add up to 16 out of 16? They have to add up to 1, right? They have to add up all the way to 1. Okay. So that is what we call a probability distribution. Now, number 3 says, what is the value of the lowest probability in the distribution? What's the smallest value? 1 out of 16. That's our lowest, right? The highest one is 6 out of 16. And they're between what 2 integers are these values? 1 out of 16 and 6 out of 16, between what 2 integers? They're both between 0 and 1. Are they always going to be less than 1?
That doesn't make sense.
No?
6 is not between 0 and 1.
No. 6 out of 16 is. 6 out of 16 is a decimal, Rowan.
Oh, I thought you
Right? They're all of those fractions are less than 1. Right? Because 1 is equivalent to a 100% chance, right? So they have to be less than 1. Can't have a greater than 100% chance of something happening. So they're all between 0 and 1, and their sum is 16 out of 16 are equal to 1. Now, do you guys have a picture of the histogram? No, you don't, do you? Okay. If you were to draw a histogram, do you guys know what a histogram is, by the way? Maybe not. Okay. If you were to draw the histogram, you'd have 1 out of 16, 4 out of 16, 6 out of 16, 4 out of 16, 1 out of 16. A bar graph. Is it symmetrical, Luke? When I say symmetrical, do you know what that means?
Yes, it's symmetrical.
What does that mean, to be symmetrical?
I don't know, Brandon, what does it mean?
Oh, Brandon, what does it mean?
Same on both sides.
Same on both sides, exactly. If I were to put a mirror down there, would it look the same on both sides? And the answer to that is yes. It's perfectly symmetrical, isn't it? I'm going to draw something on here that I'm not going to explain. I'm just going to draw that to give you an idea of what is coming in the future. Okay, sure, we'll call it the wave. Okay, part B says estimating the probability distribution. This is the theoretical distribution. Brandon knows why I did that. This is the theoretical distribution. Part B says estimating the probability distribution. Work with a partner, have one person toss 4 coins and another person record the number of heads. Repeat this experiment 50 times. We've done that sort of thing already. I used a program and did it for you. Okay?
I like that.
You like that?
Smart.
Oh, yeah? To save a little time. Use the results from exercise 1 to calculate the experimental probability for each outcome as a fraction. Record your results in a table. Do not reduce the fractions. How do the probabilities compare to those calculated in exercise 2? Before we do that, let's go back. Sorry, I know you flipped the page. Let's go back. It said do not reduce the fractions, but let's write them as a decimal. Can you do this for me? Can you go 1 out of 16? 1 out of 16 is 0.0625. Just fill that in right there. 4 out of 16, well, that's a quarter, isn't it? 0.25. 6 out of 16 is 0.375. 4 to 16 we've done. 1 out of 16 we've also done. Remember, this is the theoretical distribution. This is the true value. 0.0625, 0.25, 0.375, 0.25, 0.0625. So now what we're going to do is we're going to flip the coins, pretend to flip coins. We're going to use this program that I did already. And we're going to figure out this is random. Okay, I didn't just make these up. This is random. This is what you actually get when you flip the coins. Okay, so how many flips did I do here? Did it say how many flips you're supposed to do? 50, right? So everything's out of 50. Everything's out of 50. What kind of table is this? Remember the tables we did yesterday? What kind of table is this from yesterday? Roland, do you remember? We had the data list yesterday, and we had...
The ones that have 2 is called the...
Yeah. Starts with an F. Frequency table or frequency list, right? This is a frequency. So this is on the left-hand side is the number of heads, and the right-hand column is the frequency. In other words, when I flip 50 coins, how many times did I get 0 heads? 2 times. So my outcome here, probability, 2 out of 50. 11, this is not hard, right? 11 times, 11 out of 50, I got 1 heads. 20 times out of 50, I got 2 heads. 16 times out of 50, I got 3. And 1 time out of 50, I got 4. As a decimal, 2 out of 50, 0.04. 11 out of 50 as a decimal, 0.22. 20 out of 50 as a decimal, 0.4. 16 out of 50, 0.32, 0.02. Remember, this is the experimental probability distribution. All these big words. Experimental probability distribution. Should those numbers, Janelle, should those numbers have matched these ones from here? Well, sorry. These numbers here, the decimal versions. Should these decimal values match these ones? You don't know? They should? Why should they, bro? It's the same experiment, right? This is just theoretical. This is what actually happened. Is it always going to be exactly these numbers? Like if you flip 50 coins, would you get the same numbers? You'd get different, right? But more or less, they should be close. Are they kind of sort of close? 0.06, 0.25? Are they kind of close? Yeah, close-ish. They're close-ish. The lowest number was 0.04. The highest number was 0.4. They're always between 0 and 1, and the sum, once again, is 1, right? Or 50 out of 50. Here's the histogram. Is this symmetrical, Brett? Is this histogram symmetrical? It's not, eh? Is it kind of, sort of? On a scale of 1 to 10. 6? Wow, that high? Okay. Thought you were going to say like a 3. It's kind of, sort of symmetrical, but not very perfect. No, won't look the same, but it's kind of, right? If I were to do it instead of 50 times, and this is why I didn't want to do it for you, if I were to do it again, but this time I'm going to do it, how many times here? 1,000? If I were to do it 1,000 times, and you don't need to fill these in, are these values going to be closer? It's 34 out of 1,000. What's 34 out of 1,000? 0.034. Is this more symmetrical?
Yeah.
Yeah, right? The idea here being that the more times you do the experiment, the closer your experimental probability should be to your theoretical. Okay? So the idea is that when you do experiments many, many times, you get close to the theoretical. The theoretical should predict what will happen. Does it always predict? Not perfect, but it should. That's the basic idea. Just had to go. Purple box on the bottom of page 99. A probability distribution gives the theoretical probability for each graph outcome of an experiment. It can be displayed as a table or graph. Here are two important properties of probability distribution. They're always between 0 and 1, and the sum of the probabilities is always equal to 1. That's what I had to get through. All right, not exciting stuff, I know. Flip the page. Page 100, Lacey, is where we're at. And in fact, you need this handout right here. Oh, give you one? Okay, good. On the back side, you can take a couple notes here, because there's a little bit of room. Okay, on the back side. Top of page 100. The estimate of a probability distribution gets closer to the true probability distribution as the number of repetitions increases. And once again, if you do the experiment many, many times, you get closer probability to the theory. A uniform distribution is not what Mr. Thacker hands out the football jerseys. Thank you. A uniform distribution is a probability distribution in which the probabilities are all equal. Scott on? Yeah. Uniform distribution. Okay, it's a probability distribution in which the probabilities are all equal. For example, an experiment consists of tossing a single six-sided die and noting the number on the face of the die. The possible outcomes of this experiment are 1, 2, 3, 4, 5, and 6. And the probability or the chances of each of these outcomes is 1 out of 6. When you draw the histogram, what does it look like? Each bar is exactly the same. This is what we call a uniform distribution. A uniform distribution, all probabilities are the same. In a uniform distribution, all of the probabilities are the same. Okay. A binomial experiment. Brett, do you know what the word binomial means? No? The prefix bi tends to mean two. Binomial means that it has two things to it. Okay? Like a bicycle. A binomial experiment has a fixed number of independent trials in which the outcomes can be classified as success or failure. Now it's taken me years and years and years to come up with a proper thought in my head of what a binomial experiment is. If you don't get it off just by reading that sentence, you are not alone. It's taken me a long time to figure out what exactly it is. I will do my best to give you an idea what that is. The experiment in the investigation is an example of a binomial experiment. Why is the flipping the coins a binomial experiment? It's because, well, there's two outcomes, and it's not heads and tails. It's you either got the two heads or you didn't get the two heads, or you got the three tails or you didn't get three tails. That's what it is. It's really hard to explain, and I'm going to have to go through a little bit more. Okay? And that's what they're talking about in example number 1. Okay, now did I do that? No, I didn't. Okay, so example number 1 on page 100. Classifying probability distributions. A six-sided die is tossed 2 times and the number of sixes is recorded. A card is drawn from a well-shuffled standard deck of cards and the suit is recorded. Construct the probability distribution for each experiment. Classify each distribution as a uniform one, a binomial one, or neither, because it could be neither. So let's look at the first one. The first one is a six-sided die tossed 2 times and the number of sixes is recorded. So you've got your sample space, and you guys don't need to jot this down, but you've got your 1, 1, your 1, 2, your 1, 3, and so on. Okay? You are to record the number of sixes recorded. Okay, so how many possibilities are there? There's number of sixes, the probability. You could have 0 sixes, you could have 1 sixes, you could have 2 sixes. I'm looking at that grid on the top of page 101. How many different ways can you get no sixes? 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2. There's a lot of ways you can get no sixes. How many are there? If you count them all up, there's actually 25. There's 25 out of 36 ways you can get no sixes. How many ways can you get exactly 1 6? If you count them up, there's 10. How many ways can you get exactly 2 6s? There's only one. 6, 6. There's only one. If I were to graph that, would you get a symmetrical histogram? No. Okay? Let's go down to number 2. Because we were supposed to find the probability distribution, which we just did, and then we're supposed to classify it as uniform, binomial, or neither. It's fairly easy to say whether it's uniform or not. If it's uniform, they have to be all the same. Are they all the same? They are not. Is it uniform?
No.
No. So it's either binomial or neither. Is it binomial? Is there success and failure? No. This is hard. This is confusing, I understand. There is success or failure because you're counting the number of 6s you're counting if you got 0 6s. You either get 0 6s or you don't get 0 6s. That's your success and your failure. Okay? Is there a fixed number of trials? Did we flip it a certain number of times? 36. This is a binomial distribution. Okay? They will not ask you this on the exam. They will not ask you define a binomial distribution. Is this a binomial distribution? They will not ask you that. The only reason I need to go through it is because if you flip ahead, you go way ahead to about page 126. Tutorial 3.5 says the normal approximation to a binomial distribution. You have to know whether it's binomial or not before you can do the normal approximation to it. And I realize I might as well be speaking Chinese to you right now, right? Yeah, I realize that.
Okay.
Speak Chinese to you? No. Not unless it involves chop suey or a fuyang. Yeah. Or chicken, Cantonese chicken chow mein. That's my favorite. Cantonese chicken chow mein. That's what that is. Okay. So that's the only real reason that you need to understand what a binomial distribution is. Now, what about the card being drawn? I don't think we need to go through the card being drawn too much. Okay, and you'll notice there that they've got the answer. We've got spades, clubs, hearts, and diamonds. 13 out of 52, 13 out of 52, 13 out of 52, 13 out of 52. Clearly, what kind of distribution is this? They're all the same, so it's a uniform distribution. Yay, that's the easy one, right? That's the easy one. Awesome. Okay, now, this is, if I haven't blown your mind yet, I'm about to.
You guys teach us how to count cards?
Pardon me? Can I teach you how to count cards? Not in 20 minutes, no. Could I actually teach you how to count cards? Probably with enough time, yeah.
Really?
Yeah. We could probably make an app for that, Brandon, actually.
Yeah, you can't just brag that.
No, they don't let you do that, no. No. But you could make an app for that.
Make it out for it.
It'd be pretty easy, really.
Yeah, cards count.
Eh?
You have an app, and you just do it.
I know. Like, there's not much to it. It's the fact that you're doing it in your head.
Yeah.
Okay. So we can use the binom PDF command. It's a command on the graphic calculator to generate a binomial distribution. Who had fun making these? Did anyone have fun making these? No? Hard to believe. Even I had a hard time putting my hand up when I said who had fun. Nobody has fun making that, especially if I made it even harder. Okay? So I'm going to show you how to do it on the graphic calculator. So flip to Utility 27. I don't know what page number that is. You got to go to the back. Page 349. Page 349. Okay? I promise once I go through this, I will stop talking. You're wishing I could stop talking earlier, aren't you? Come on, Bob. Come on. Trust me, I'm not having a whole lot of fun either. Using the TI-83 to calculate and graph a binomial distribution. The first thing you need to do is you need to clear out your lists. Step number 1, go to Stat, go to Edit, clear out your L1 and your L2. Well, as long as you got L1 and L2 cleared out, you're good. All right. So what we're going to do is, instead of having to do the tree diagram and the flips and figuring it all out, counting, we're going to get the graph calculator to do the probability distribution for us. Okay, for a binomial, a binomial distribution. Wow, this sounds exciting. When Mom says to you at home tonight, what'd you do in math day? You can say, we used the graphing calculator to graph and calculate the probability distribution for a binomial distribution. I can't even say it. I'll be sure to tell my wife when I go. The TI-83 can be used to calculate the probabilities for a binomial distribution. All right. The results can then be displayed in a table form using lists or graph as histogram. The syntax is binom PDF, number of trials, probability of success on each trial. Don't worry, I'll show you what it means. To illustrate this feature, consider an experiment in which a coin is tossed 12 times. Does anybody want to do a tree diagram for tossing a coin 12 times? No, we don't want to do that. Sounds bad. On each toss, the probability of getting a head is 0.5. In such an experiment, what are the probabilities of getting 0 heads, 1 heads, 2 heads, 3 heads, 4 heads, all the way up to 12 heads? Nobody wants to do that by hand. Here's what you do. Okay, obtain the binom PDF. It's under second vars. So we've cleared out our lists. We're going to go back to our home screen now. Cleared out your list. Go back to your home screen. You have to find the binom PDF command. It's second function vars. Do you see what's above the vars button? Distribution.
Yeah.
Second function vars, and then pick the one that says binom PDF. This is the world you're going to live in for the next couple of weeks. It's way down at the bottom. Now there's two of them. Be careful. There's PDF and there's CDF. PDF stands for probability distribution function. Shocking. Bobby, go to the limb here for me. CDF, what do you think? I bet you can get the second letters. That PDF is probability distribution function. CDF, cumulative distribution function.
Yeah, I know.
I thought you could get the D and the F though. They're the same thing. Oh, CDF stands for cumulative. Don't pick that one. Okay, pick the PDF one. The first one.
Just 0.
Yeah, it's 0 on some of your calculators. It's A on others. So make sure you get the right one. Binom PDF. Go ahead and pick that one. This all seems really complicated. I understand that. When you're all done, it really isn't that bad. Okay, it really is. It really seems overwhelming. It's not that bad when you see it all. Okay, so you pick binom PDF. Now the syntax, that's like the order of things that have to come, is number of trials and probability of success on each trial. How many coins are we tossing? Sorry, how many times are we tossing the coin in the question? 12, right? It says that in the question. Consider an experiment in which a coin is tossed 12 times. So I just put 12. I put 12. Okay, I put 12. The next thing you have to put is the chance of success. We are counting the number of heads. Roll, when you flip a coin, what's the chance of getting heads? 50%. So you just put 0.5. You just put 0.5. That's, you got to put a comma. That's all you got to do up to now. Binom PDF, bracket, 12, comma, 0.5. I think you have to end the bracket. Okay? If you press enter, and you can go ahead and press enter if you want, you're going to get a bunch of crazy numbers that mean nothing to you. Okay? Now, you don't really want those crazy numbers just like that. You want them in a list where you can read them. How can I take those crazy numbers and put them in a list, Mr. Bennett? It's easy. You could just write them down and punch them in, but that would be stupid. Don't do that. That's foolish. Don't do that. Here's what you do. Find the button that says STO on it. From the stove. Store is what it means. It's abbreviation for store. We're going to store that number, that list of numbers. We're going to go store. You see it says answers arrow. I want it in L2. So I just simply go second function L2 and put the answers in L2. Put the answer in L2. Press enter, and it's very exciting. Nothing happens. However, if I go to L2, go stat. I say go to stat, edit. Guess what's in L2? Those numbers. Now, what we've done is we've created the probability distribution for flipping a coin 12 times. What excitement. We're almost done. How do I know what those numbers refer to? Why did I leave L1 blank? Because L1 is for? Start with 0. Why start with 0?
Because 0 comes first.
Thank you. Because there is a chance that if you flip a coin 12 times, there is a slim chance that you wouldn't get any heads at all. Right? So I get 0, 1, 2, 3, 4. I know you guys can count.
7.
Some of you. Now, you have to make sure, this is actually a good little tip here, you got to make sure that the number of numbers, like, you got to make sure that they're balanced, right? There's 12 here, there's 12 there. Actually, there's 13, isn't there, right? 0 to 12. You got to make sure that there's the exact number. What you've got is the probability distribution for flipping a coin 12 times. If I said, Rowan, what are the chances of flipping a coin exactly 12 times and getting exactly 4 heads? Could you do that? Yeah, it's 12%. Would you want, oh, no need for applause. Would you want to do a tree diagram for that? No, it would take forever. Can you imagine drawing it and then having to count them all?
For 1 mark.
Yeah, not happening, right? Not happening. Now, if I were to graph that, and I'm not going to bother showing you, but if I were to graph that, would it be one of those nice, perfect, symmetrical ones, or would it be just sort of a kind of symmetrical? Do you want to see the graph? I can do it if you want.
Really?
No?
Not very, no.
I can do it relatively quick.
Okay, go.
Give me a second. Let's just go through this, because every kid really wants to know this, right? What are the chances?
Yeah.
Right? Give me about 5 more minutes, and then I'll stop talking for the rest of the day. I promise. Yeah, you're right. Okay. I promise. Here's how to do it. You're going to take your graphing calculator. You're going to go back to your home screen. You're going to go back to your home screen. Here we go. We're going to go second function distribution, binomial PDF. Binomial PDF. How many flips was there? How many guesses were there? 25 questions. So, 25. What are your chances of getting the question right? 0.25, because there's 4, right? 4. Yeah, that's true. 0.25. Now, you didn't need to do this, but you can do it all in one step. You don't have to enter. You can just go store L2 right from there. You can do it like that if you want. Okay? Store L2. Press enter. Nothing happens. In L2, something happens, right? Stat, edit, L2, right? Those are the new numbers. Now, Rowan asked a good question. He asked, do I start at 0 or do I start at 1? Because there's only 25 questions. But there is a chance that you could do what? Get them all wrong, right? So you have to start at 0. You always start at 0. Okay? Always start at 0. In fact, what is your chance of getting none right? 7.5 E minus 4. 0.00075. About 0.7% chance of getting nothing right.
That would be a crappy day.
Yeah. So this should go all the way down to, it only goes to 12 because I haven't changed from last time, but it really should go to 25, right? Should go all the way down to 25. And it does. What are your chances of getting exactly everything right? 25. Your chances are 9 times 10 to the minus 16. 0.00000, how many zeros? 15 actually. 15 and then a 9. What every kid really wants to know though is what are the chances of you actually passing?
So you don't have to.
Out of 25, I guess you'd have to get 13 right.
What's our chance?
So what are your chances of actually passing? If I go to 13, it's, oh, hold on. That's not right, is it? Your chances of passing are 0.002, 2.2%?
You guess them all.
Is that what that means? I'm leading the wrong way, by the way. I'm making a mistake here. What's wrong? That can't possibly be right. Your chance of getting 13 out of 25 is 0.00245? That's true. But your chances of passing are a whole lot more, aren't they? What's my problem? What's going on?
What's your computer there?
No, everything's exactly right except I'm not interpreting it right. I asked what's the chance of passing. This shows what are your chances of getting? Exactly 13. But passing is 13 or 14 or 15 or 16%. So what do I have to do? I have to take this one and add it to this one and take it and add those all up. Who wants to do that?
Nobody.
Nobody. Which is why we don't have the PDF one. We also have the
CDF.
which stands for
Cumulative.
what means cumulative means add them all up. So in fact, if I did this, if I were to go second function distribution, and you don't need to know this, now I'm just having fun. Yeah. This is what I do on a Friday night.
Oh, yeah.
Please don't believe that.
Party.
25, comma, 0.25. You guys really want to know. I know you do. Store that into L2. Now, I've already done the other part, so it should be right there. Okay, so what are your chances of getting exactly a 13? Whoa, that's not right, is it? You have a 99.9% chance of passing if you guess.
Nice, man. Yes,
The cumulative doesn't work that way. The cumulative is the opposite. Okay, yeah. What this they don't add from 13 on, they're actually adding from top to bottom. So you have to look at it the opposite way. What are your chances of getting 12 or less? 99.6. That means that your chance of passing is 100 minus 99.6, 0.4%. If you guess at random, completely at random, on 25 questions, 4 answers, right? 25% chance of getting each one right, you have a 0.4% chance of passing. Moral of today, don't do that. Oh, you be quiet with your invert norm, Mr. Fancy Pants.